All right, recording. So last time we were talking about this business right here. We're talking about boundary flux. And keep in mind, boundary flux refers to a boundary of a two-dimensional region. Keep in mind further this word boundary. Now a loaded word. Boundary always means oriented. And it means oriented according to certain conventions, which again are arbitrary, but then again are also standard, and so they're not optional. Boundary in this case means outward. Okay, so we did some preliminary setup work and talked about the direction of the outward vector and rotate 90 degrees and all that, leading to a nice little tool that we're going to be making use of momentarily, that we actually did make use of last time. And the idea was that if you take your boundary curve over which you're computing the total boundary flux, and if you chop that up into little pieces, the whole is the sum of the parts, right? Then you can look at the resulting integral that we don't know how to compute because we've never seen in DS before, right? That's not part of any of our formulas for how to compute any kinds of integrals that we've previously seen. But with this little slick move right here, knowing that f dot n equals f perp dot t allows us to rewrite it so that yellow integral becomes this orange integral, and the orange integral we know how to deal with. We have seen this before. TDS, we know exactly what that is. That is the dx vector, right? And so we have been able to turn then a brand new unfamiliar flux integral into a good old-fashioned, regular old vector line integral that we have formulas and tools and experience, etc. And the only price to be paid is that we're not looking at the same vector field, of course. We're looking at this new vector field called f perp. And I believe this is where we finished last time. Okay, so how do we compute this line integral? And I'm going to go ahead and zoom in so we can see a little bit better. How are we going to compute this vector line integral? Well, notice in particular this is a boundary vector line integral. That was the whole point. We're computing boundary flux after all. And so being as it is a boundary, we can apply Green's theorem. Green's theorem says that I can compute that as a double integral of Green's operator over the interior region. Okay. Is everybody with me so far? Everybody's happy. All right. Okay, so moving along, and let's proceed with this calculation. What are we going to do with Green's operator here? Well, Green's operator, we have a formula for Green's operator. Green's operator is the x partial of the second component minus the y partial of the first component. Now, we usually phrase that as dq dx minus dp dy, but that's the confusion of variables situation. That's if your vector field is p comma q. To be more careful about it, when you're taking a Green's operator of a vector field where there might be a confusion of variables, remember it is the x partial of the second coordinate, which is p in this case, minus the y partial of the first coordinate, which is minus q in this case. Right, so so you got to be a little bit careful. That's one little tricky bit. But writing down Green's operator gives us this formula here, and then I can observe that minus of a minus is a plus. That's convenient, and lo and behold, check it out, my integrand, it doesn't look like Green's operator anymore. It's certainly not Green's operator of f, but it is exactly divergence of f. Flashing back to chapter 3 where we defined divergence. And we previously defined divergence as sort of, in some sense, without any context or justification or motivation. And I made some vague statements about it, computing the amount that a vector field is kind of flowing outward from a region, right, without justifying it. So here's our first instance of seeing divergence come up naturally in an argument. And specifically this nice punchline, which we call the two-dimensional divergence theorem, tells me that outward-oriented boundary flux is a double integral of divergence over the interior. Okay, how are we doing? Does everybody follow me? Everybody's happy? All right. So there's a couple of ways you can think about this. First point of view I'm going to take is clearly the step that where we did the real heavy lifting, right? The big the big move in this argument was Green's theorem. Green's theorem did most of the work. This business right here was kind of playing clever little geometry games, and this business down here is just kind of rewriting some algebra. So Green's theorem is doing most of the work, and as such, the 2D divergence theorem can be thought of as just kind of a variation on Green's theorem, and that's a nice way to think about it. That is, it's a good thing. What we're going to see very soon on the next page is that the 2D divergence theorem can also be thought of as its own theorem, on its own, independent of Green's theorem. We'll get there in just a moment. But furthermore, yet a third way you can think about this result is that it's a precursor to the big divergence theorem that we're going to be getting to in Chapter 7. The three-dimensional divergence theorem. That's the one that has most of the big applications. That's where divergence is really going to be a powerful tool. And structurally it looks just like this. Everything's three-dimensional though, so everything's a little bit different. Okay, so let's do a quick application. Here we go. This is a example computation. Suppose I want to compute flux. That, by the way, when you're asked to compute flux, if it doesn't indicate to anything to the contrary, assume outward oriented. Right? So here we're computing the flux outward through the unit circle, and we've got a vector field given. And how are we going to do this? Well, again, this integral here that we've been asked to compute is something we don't really have any tools for particularly. And the whole trick of what we did in the above theorem is to rewrite it in terms of something else, right? And so we're going to do the same thing here. I'm not actually going to compute that directly. I'm going to observe that what it is just a double integral of divergence. We're going to capitalize on the fact that we've already done all this work up here. And so here we go. Flux is a double integral of divergence. There's our 2D divergence theorem in action, right? And conveniently, divergence is easy to compute. We're going to take the x partial of the first component. We're going to take the y partial of the second component. Lucky break, all of the ugliest parts of the vector field disappeared. Those partial derivatives, right? So I call it lucky. It wasn't lucky. I manufactured this example to be lucky. I like the first example to be a sales pitch on how useful the theorem is. And so this is the kind of good fortune that you can hope for. It won't always be this nice. But anyway, so nice convenience in how the algebra worked out. We end up with an easy double integral as evaluated with some simple geometry. Okay, how we doing? Everybody okay? All right. Okay, moving along. Now, I made this claim that you can think of the 2D divergence theorem as its own theorem, that it is also an accumulation theorem. And if you look back at how we did Green's theorem in the first place, the two big steps that we used in developing Green's theorem was we developed the idea of accumulation. We established that the object in question, namely circulation, was an accumulating quantity. And then we wrote down, and I swept the details under the rug, right? But we wrote down that there was a corresponding notion of density, and that quantity, namely circulation per unit area, namely circulation density, was just Green's operator. So you can do the same thing for boundary flux. And the very first observation, arguably the key observation, is that boundary flux is also an accumulating quantity. It behaves like stuff. It behaves like a mass or a population. It behaves like stuff distributed over the interior. We compute it on the boundary, of course, but it behaves like it's distributed over the interior, and in very meaningful senses it really is. And so to see that this is an accumulating quantity, we can look at this picture here. For this region on the left, This is what outward-oriented boundary flux looks like. That's for the green region on the left. Outward from all sides. Right, now let's look at the blue region over here on the right. What does outward-oriented boundary flux look like here? Well, again, outward from all sides. That's outward-oriented boundary flux of the right. How does that relate to outward-oriented boundary flux of the whole? Well, got a lot in common, right? All of these exterior edge, right? It's all the same. Green is the same as purple. Let's see here. Green is the same as purple along in here. So they cancel. Green is the same as, blue is the same as purple along in there. So all of that cancels. The only thing that doesn't cancel immediately is this business here. This right here is the different. This is the problem. This is the impediment to claiming that boundary flux is an accumulating quantity. And if you look at this impediment, what you notice is that this impediment consists of this edge, right? Flux through that edge, computed twice, once oriented that way, once oriented with the exact opposite orientations, and so those two fluxes cancel. Right? Appears twice with the opposite orientations, and they cancel. What's wonderful about this is that sort of structurally, if you will, this is kind of the exact same way it went down when we were talking circulations. With circulations, that edge appeared twice with opposite parallel orientations. One up, one down. Here it's appearing with opposite orthogonal orientations. One to the left, one to the right. Still opposite, and they still cancel. So we have an accumulating quantity, and you can go through and make all of the exactly analogous arguments that we did with Green's theorem, and the result will be the 2D divergence theorem. You'll get this exact same formula without having to make any direct reference to Green's theorem at all. So, again, connected to Green's theorem, but also it is independent of Green's theorem. So, beautiful fact. Okay, so I like to summarize. We have a couple of different accumulation theorems, sort of new accumulation theorems now, all of which are extremely analogous to what you could argue is our first accumulation argument, right? It was mass. We didn't even use the term accumulation there because, well, of course, mass is the whole is the sum of the parts. That's just physically intrinsic to what mass is. And so mass is an accumulating quantity, whole is the sum of the parts. Mass per unit area is density. Let's be a little bit more careful about that. Accumulating quantity, in this case we're talking about mass. Per unit size, in this case we're talking about area. Quantity per unit size is the mass notion of density, which we call mass density. And then all of what I just said there also applies to Green's theorem. Circulation is an accumulating quantity. Circulation per unit area. Green's operator is just circulation density. It's accumulating quantity per unit area. Just like mass density is a different accumulating quantity per unit area. And then, as we just developed, the 2D divergence theorem, again, it's an accumulating quantity. There is an associated notion of density, divergence in this case, and again, common terminology used here. Common terminology used, flux density. Now, just as a little cultural note, this term flux density, not rare. It's extremely common. In fact, when I was an undergraduate second major in physics, in those physics classes, I'm pretty sure, from my memory at least, I heard my physics professors say the term flux density more than I heard them say the word divergence. Very common terminology. And I love this terminology because it goes right to the point of why is it that we're interested in divergence in the first place. It's because it is representing this accumulated quantity per unit area. right? Flux density says exactly what it is that is the role that divergence is playing here. Right? It's absolutely beautiful terminology. Could not be better. Dig it. That said, this terminology here, not particularly common, or at least not in my experience that I have had, but it's just as natural. It's just as natural. It's just as meaningful. It's just as important to understanding the theorem that it connects to. So anyway, I'm pitching this as in addition to this, which again you can't get away from. You're going to hear flux density. That's unavoidable. Okay, all right. Is everybody okay? Everybody happy? All right. Now, so we've got count so far. We've got 2 accumulation theorems. I like to call these accumulation theorems because again, that's ultimately what they are, right? Whole the sums of parts, kind of the foot in the door. I claim we already know a third. Y'all knew a third. Arguably, you could call it the first, I suppose. But anyway, it's our third on our list here. You knew a third accumulation theorem before you showed up to this course. And that's the fundamental theorem of calculus. Fundamental theorem of calculus, it's not phrased in that way, but it is an accumulation theorem. There is a notion of accumulation in play. There's an accumulating quantity that's being computed, and there is an associated notion of density. And let me walk y'all through that point of view real quick. I think this is a very valuable point of view in trying to get intuition for Green's theorem and the divergence theorem and the future accumulation theorems that we'll be talking about as we move along. So first of all, what is our accumulating quantity? Our accumulating quantity is what I'm going to call change. It's things that look like this. If there's some function f in play, you can talk about how much it changes between 2 input values. So between x1 and x2, this formula right here says how much f has changed. Right? So change, I think it's a pretty easy pitch that's an accumulating quantity. Think about any function. And if you know how much it changes between here and here, and if you also know how much it changes between there and there, well, grand total, that tells you how much the function has changed from here to here. I mean, it's just, it's very natural. You can think about, and my favorite sort of personal example is, my height as I was growing up. So when I was 5, I was this tall. And then when I was 10, I was this tall. So this right here represents my change from ages 5 to 10. Well, then when I was 15, I was this tall, let's say, I don't know, something like that. So this is my change between 10 and 15. Altogether, this plus this gives me the total amount that I changed in height between 5 and 15, right? I mean, the change keeps adding to itself, you might say. So very naturally, it's an accumulating quantity. So that gives us the first thing that we can write down here. Total change is a sum of little changes that you accrue along the way. Now you can think about it in terms of bank accounts. If you want to know how much has your bank account increased, let's hope it increases. How much does your bank account increase total? Well, look at how much your bank account increases every day and add up all of those increases, and that gives you the total amount that your bank account has increased. All of these things I think are very believable. Next, there is a natural relationship between output change and dx, which I'm going to think of as input change in a way. Right? And here is the way you can think about this relationship here. The thing that you multiply by input change to get output change, which of course we know is the derivative. And if you look at this little part of a graph here, for example, and we know one point of view you can take on the derivative is rise over the run. And if you think about it, the rise represents a change. Here, let me do it like this. Actually, it represents change. Right? How much does the function change between the left side versus the right side of that little run there? Right? And then what about the denominator? What is this run? Well, you can think about that run as a input change, I suppose, but notice you can also think about this run as being a size. dx is a size. It's how big is that little piece of your domain. It's literally a size. Right? So you can think of derivative as a slope, namely rise over run, and there's nothing wrong with that. I'm perfectly happy for people thinking of derivative as slope in the graph context, of course. Right? That's fine. Slope is fine. Velocity, we think of derivative as velocity. That's nice too. There's other points of view you can take on derivative. I'm pushing here now a new point of view on the derivative. Don't think of, for this purpose, don't think of the derivative as a slope. Don't think of it as a velocity. Think of it as change per unit size, accumulating quantity in question per unit size associated to the piece of the domain I'm looking at. And when you have an accumulating quantity per unit size, that is what we mean when we say density, right? Oh, whoops, wrong color. Purple. That's what a density is. That's kind of a weird point of view, right? I mean, that you've probably never thought of derivatives that way. There's never been a particularly good reason to think of derivatives that way in the past. But you could, and in this case, it's awfully handy. Is everybody happy? Weird though this is. All right, so let me show you why I think this is really nice. What I'm doing, of course, what I'm doing is I'm setting up an analogy, right? We have this couple of new theorems that we're trying to make sense out of. Green's theorem and the 2D divergence theorem, and there's some mysterious aspects of this that I've been pushing that you might seem a little sort of creeped out by. The big one, I think, is let's talk about circulation. Let me go back a couple of pages here. And I suggested here that even though we compute circulation on the boundary, that you should think of it as happening in the interior. This is an eyebrow raiser. It's seemingly counterintuitive that it's a claim it's happening in the interior, even though we computed on the boundary. So let me now take this concept of how could something that's computed on the boundary be thought of as actually happening in the interior? Isn't that kind of wrong? Doesn't that seem kind of counterintuitive? Well, think about that exact same statement now in the context of the fundamental theorem of calculus. Here we go. So we've got a function, some sort of a function here. It's looking at the graph of a function, moving along like that. Where's change? Our accumulating quantity called change. Where is change? Well, it's that amount. That's the change. That's how much the function changes between A and B. Where is it computed? Well, it's computed by literally looking at f of B and f of A and subtracting. It's computed by looking at the boundary. Right? The formula, how I compute change in the first place, f of B minus f of A, is computed by looking at the endpoint and the starting point. That's the boundary. Computed on the boundary. And now I ask rhetorically, is that where the change actually happened? Right? Let's just think intuitively now. If I'm looking at this function here, where is it that this function changes? And I hope nobody's weirded out if I say, well, look, there it is. That's where the function changed. You can see it in the process of changing along in there, right? So the function changes at these points in the interior of the given interval. Right, so this is actually an extremely relatable example of something that is computed on the boundary. Right? The formula for our accumulating quantity is explicitly on the boundary. And yet it's perfectly clear that it happens in the interior. Right? So this concept that's so creepy and unsatisfying and seemingly, wait a minute, you want me to what now? right? In the context of Green's theorem, computed on the boundary, circulations computed on the boundary. I'm asserting counterintuitively that it happens in the interior. Perfectly believable for this other accumulation theorem, fundamental theorem of calculus. So the point here, why am I pointing this out? My hope is that you'll be able to take, with the, I hope intuitively satisfying idea here that change is computed on the boundary, but it actually happens in the interior. Of course it is. Look at the picture, right? And to the extent that you're satisfied with this point of view on this accumulation theorem, maybe you might be more comfortable then with this point of view on this other accumulation theorem. So that's my first motivation there. Okay, now the other motivation. Not only do we have motivation for thinking about the accumulating quantity happening in the interior, but look at what F prime does. F prime numerically, right, algebraically computed, gives us a numerical assessment of literally how much change is happening specifically where in the interior. For example, if I want to know, let's see here, I'm trying to get this all on the screen. If I want to know at this point right there, how much change is happening, generally speaking, at that point? Well, I can kind of look at the graph, I can look at the slope of the tangent line, and I get some sense for how much it's changing. The derivative is an algebraic way of getting a numerical representation of what I can geometrically see is how much the function is changing near that point, right? And I can look at a different point over here, let's say, and there, geometrically, I can see that the slope is greater. There's more change happening in the vicinity of this second point, and that'll be numerically represented by the fact that this algebraic object, the derivative, will be greater at that point. Right? So the derivative tells us literally how much of this accumulating quantity is where in the interior. That's just a phrasing of what I think is pretty familiar ideas from single variable. Here's a seemingly too easy to be useful example of that point of view. Let's look at this function right here. And on this interval from 0 to 3, well, the function starts with value 0, it ends with value 9, it changes by a grand total of 9. Let's ask the question now, how much of this accumulating quantity, how much of this total amount of change that I've detected on the boundary, how much of that is happening at this point 1 versus at this point 2? There's more happening at one point, less happening at the other point. Which one has more of the change happening there versus the other one? And, well, we answer the question by just looking at change density. Right? The derivative. The derivative is the giveaway. The derivative points to how much of the accumulating quantity is happening where. So I evaluate that derivative at these 2 points, and easily observed, this value 4 is greater than the other value 2, and so it is at this point 2. Right? X equals 2. Between these two options, x equals 1 and x equals 2, it's at 2 that there is a greater amount of change happening. A greater amount of this accumulating quantity is in the vicinity of 2 compared to at the vicinity of 1. And again, that seems like an oddly awkward sort of phrasing. But that's an interpretation you can make of the derivative. Now again, why is my goal here to teach y'all single variable calculus? No, of course not. Y'all know all of this previously. But let's apply the same ideas now to Green's operator and to divergence. Right? And in the same way that you can kind of look at the picture and you can kind of convince yourself, clearly I see less change happening there and more change happening here. Wouldn't it be nice if there was an algebraic representation of how to quantify that? And there is, and it's the derivative, and that's this example. Well, likewise, let's look at circulation. Right? Circulation looks like, well, something kind of like this. Circulation is computed on an oriented curve. There's the oriented boundary of our, we've got a solid rectangle here. I can compute, I can measure circulation on that oriented curve. You get some value. Yeah, but where is that really happening? And I emphasize, even though I measure it on the boundary, that's not really where it's happening. So where in the interior is that circulation actually happening? Well, I'll tell you one thing. It is not happening in that general vicinity where I have this orange dot that I'm going to think of as being a leaf. I like to think of leaves floating on a river. The vector field represents flowing water, and I've got a little leaf that's floating on the flowing water. And let's think about what happens to this leaf as it's pushed by the water. And, well, it's pushed kind of equally, if you will, on both sides. Vector field's constant in that general vicinity. And so this leaf is going to float on down the river, but it's not going to be twisting because it doesn't have any circulation applying to it. So, in fact, this is measured geometrically by Green's operator. And if you were to compute Green's operator at this point, you would get 0. In this whole sort of upper third or so, or whatever that is, upper fourth of my rectangle, Green's operator is 0. There is no rotation happening. So this circulation you're measuring on the boundary, it's not coming from there. There is no circulation up there. Geometrically, we see it from the rotation picture. Algebraically, I see it from Green's operator being 0. Okay, now let's look at a different leaf down here. Let's say here. What's happening to a leaf there? Well, notice what our vector field is doing. Notice our vector field is small, and then it's medium-sized, and then it keeps getting bigger as you go down in this region. So on this leaf, yeah, it's being pushed somewhat on sort of the top side, but it's being pushed harder on the bottom side. This leaf is being pushed asymmetrically. It's being pushed more on the, as if you're over here kind of pushing it like that, it would feel like it's on the right, on the underside, as we see it from here. So if it's being pushed harder on the underside, I hope it's not implausible to suggest that, well, this leaf would actually be kind of turning as it floats downstream. And it'd be turning counterclockwise, because the more powerful push coming from the bottom side would tend to do that. Does that make sense to everybody? So geometrically, I can see that. Now, what is the algebraic giveaway? What measures that? Well, again, Green's operator. And if you were to write down a formula for a vector field that looks like this, if you were to compute Green's operator, it would be positive in this gray region. So again, we've got this purple circulation, total circulation on our rectangle. Where is it happening? It's not happening up here, where the white background is. There's no circulation happening there. It's happening in here, in this middle sort of chunk, right, this middle half, as it were, where Green's operator is positive. Positive value of Green's operator is saying there is a twisting in the fluid that's happening in this region. That's where this circulation measured on the purple outside boundary is actually coming from. Right? So Green's operator is the giveaway. Everybody with me? Yep.
Is it positive because it's rotating the leaf in the same direction as the orientation of the boundary curve?
Yes, that's correct. Yeah. Well, positive specifically because it's oriented counterclockwise. So that's one of the conventions. Green's operator is based on the standard convention that boundaries are always going counterclockwise. So yeah, Green's operator is always assuming counterclockwise. Yep. Does that make sense?
Yep.
Cool. Yes.
Could we use this to calculate torque based on because it's say we have different forces put
The thing about 12, maybe. The devil's going to be in the details on that one. It's going to depend on how the forces. I could imagine a scenario where forces are being applied in sort of different ways across an entire region. So yeah, maybe. I hesitate to say anything other than maybe, just because the details do matter there. But I like that line of thinking. Yeah. All right. Okay, so in the same way that the derivative, in the same way that the derivative points to where the function is changing and where the function's not changing. Likewise, Green's operator, by its values, points to where the vector field is circulating and where the vector field is not circulating. Okay. All right. And then likewise, divergence is all about flux. So if you have, and I'm going to have to zoom out to get this all on the screen. Here we go. If you have a boundary, and keep in mind our convention boundaries when we're talking about flux. The word boundary is a loaded word. It means oriented according to convention. The convention is outward, standard convention. Arbitrary, but standard. That's where we measure flux. Is that where the flux is actually happening? Is that where the flux is coming from? No, not at all. Of course not. It's coming from the interior. There's something happening somewhere in the interior that's making the fluid have a positive amount of flux on the outside. Where in the inside is that coming from? Well, it's not coming from here. Right? If you look at that general vicinity, the vector field, well, there's the same amount of flow in as there is out. Vector field is generally constant, right? In this vicinity over here on sort of the right half, if you will. So there's no boundary flux happening there. And this would be evidenced by, if you were to compute the divergence in this region, you would find that divergence there is 0 in that region. Now I got to zoom in so we can see better here. Sorry. There we go. But what about in a region like this here? Well, again, notice the vector field is not constant in this dark gray region. You can see as I sort of move from left to right, those field vectors are getting longer as I move toward the right. So the amount of flux in on the left is a little less than the flux out on the right. So in the net, there's actually a positive outward flux out of that little orange region. And this is evidenced by, again, the value of the divergence. And if you were to compute the divergence in this gray region, it would be positive. So, sure, we have, and I should zoom out again. Yeah, we have a positive boundary flux as measured on the purple region. Of course, that's not where the positive flux is actually coming from. Where is the flux coming from? It's coming from where divergence says it's coming from. Divergence is positive. Here, this gray region, this is where the divergence is coming from. Again, as evidenced by the field lines getting longer as you move to the right, thus creating little situations where there's more going out than there is coming in. And it's not coming from over here. There's just no boundary flux in the net. There's no boundary flux happening here at all. Okay. All right, so again, you can do this purely algebraically, right? I mean, what I've done here is a kind of a geometric picture so you can get some geometric sense for it. But here's a purely algebraic version of it, where I assume we have a vector field. And we've got a rectangle. We're going to look on the boundary of this given rectangle here, and you could compute the circulation, and you can compute the flux, and what those quantities are in total isn't the point here, but there is a total circulation, there is a total boundary flux. So for each one of these, is there more happening at this point, or is there more happening at this point, right? Which one of these is there happening more? Well, if you're interested in circulation density answers the question. Green's operator is circulation density. Just evaluate that expression, and it happens to be 4 plus 6y. Evaluate that at the one point that you're interested in. Evaluate it at the other point that you're interested in. See where it's bigger. We look at these two numbers. Which one's bigger? Oh, 28 is bigger. And so because that's the bigger value, that point is where more circulation is happening between the two options. Right? So no picture at all here, no geometric intuition here. I'm just using the interpretation of Green's operator as circulation density to draw this conclusion. This is totally analogous to this example where I use the derivative as change density to draw this same kind of conclusion. Okay. Likewise, where is there more divergence happening? Excuse me. Where is there more flux happening? Excuse me. Where is the flux happening? Well, divergence tells you how much flux is happening where. Divergence is flux density. There's your divergence. We're going to compute that divergence at, well, the green point and at the orange point. We want to look and see where is it bigger. Oh, 17. That's the bigger of these two numbers. That's the larger value of divergence. That's where most of the flux is happening between these 2 points anyway. And so 3, 3 is where there's more flux happening. Okay. All right. So moving along, we're going to move on now to section 6.3. This is another another accumulation theorem. We're going to get to, it's called the fundamental theorem of line integrals. So this is, I guess, arguably our fourth accumulation theorem. And they're going to keep on coming. Before I get to that, a little point of terminology. This is, it just is what it is, but we're going to talk about a conservative vector field. It's just the word that physicists use. Conservative means that it's a gradient. I've always kind of rolled my eyes at this because to my point of view, we already have a word to describe the state of a vector field being a gradient. The word is gradient. Why do we need another word? I don't get it. I've never understood this. Anyway, that's the common terminology. Again, it comes from physics. Now, I do know what the motivation is. The motivation is that it's exactly these vector fields that allow for interpreting. If you interpret the vector field as being a force, then it's exactly these for which you can generate an idea called potential energy. And you need this idea of potential energy to be able to make statements about conservation of energy, right? And that, kinetic plus potential always adds up to the same constant, right? So that's where conservative comes from. And so, yeah, there's a motivation. But we're not doing physics necessarily. I mean, maybe we are sometimes. But when we're not doing physics, I don't see why we should use physics terminology. So anyway, for whatever it's worth, in some contexts, you will hear the term conservative. I don't really feel the need to do that. I'm going to just use the word gradient because that literally says what the vector field is. It's literally a gradient. So gradient seems like the right term to me. Anyway, that's my soapbox speech on that. So let's talk about the fundamental theorem of line integrals. Here it is. You might even feel like you kind of recognize it. Right? Doesn't that look familiar? It looks just like the fundamental theorem of calculus, structurally. That's a little different. Okay, fair. A little bit different. This is a function defined on a multivariable domain. Right? The fundamental theorem of calculus doesn't know anything about multivariable. This is a vector line integral, not a single variable integral. So that's pretty different. Right? But structurally, integral equals f of b minus f of a, you got to admit that's pretty familiar looking. Furthermore, the integrand here, if you were thinking about the fundamental theorem of calculus, that would be the derivative. Here, it's a gradient, which is a kind of a derivative. It's really similar. Does that all kind of everybody see all the similarities there? Okay. All right. One little additional bit of terminology, by the way. So this vector field, I've already observed that I'd rather call this a gradient than calling it conservative because it's literally a gradient. What do we call this function? I'd like to call it the anti-gradient. Right? If you think back to the fundamental theorem of calculus, and we have derivative and antiderivative. Same thing here. Seems to me like this function ought to be called the anti-gradient. And you're going to hear me throughout the rest of the course calling this the anti-gradient. Physicists don't use the term anti-gradient. They use the term potential function, which kind of makes sense if you're talking about physics, which sometimes we are, but again, not always. And in the cases where we're not, I don't see what the advantage is. The term anti-gradient is extremely descriptive of the role that it plays. And so I think it's better to say anti-gradient. Yeah, go ahead. Little f is the anti-gradient. That's right. And big F here is the gradient. So little f is the anti-gradient of big F. Big F is the gradient of little f. Yeah. Okay, so where does this theorem come from? How do we see it? I claim that it is an accumulation theorem. Let me persuade you that this is an accumulation theorem. For one thing, change, aka this expression, is again an accumulating quantity. Of course it is. If I look at the total amount that f changes on that piece of curve, and the total amount that f changes on that piece of curve, they add up to the total amount that the function changes on the whole curve. That's just how change works, right? You can think of whatever metaphor you like. I like to think of this being a windy mountain road, and I'm keeping track of altitude. How much my altitude changes on the green curve, how much my altitude changes on the blue curve. If you add them up, you're going to get the total altitude change on the whole purple curve. All right, so we have an accumulating quantity. Furthermore, we know how to relate output changes and input changes. We have this old rule. We have this old rule right here from chapter 2 that says if you want to know output change, how much does the value of the function change compared to input change, namely how much do I move in the domain? Well, that's what the gradient does. That is the gradient's job. The gradient here is what you dot with input change to get the output change. Again, it's just old chapter 2 reference. So we have that formula, which, by the way, of course, don't forget you can rewrite dx like this if you like. Either one of those is fine. So putting them together, and I'll come back to this business about orientation in just a minute, but real quick, I just want to get to the conclusion here first. We have agreed first that change is an accumulating quantity. Boom. The whole is the sum of the parts when you're looking at change. And each little bit of change you can think of it in either one of these senses. Take your pick. Whatever. It's all good. And so we've got then a theorem, which is f of b minus f of a, the total change in whatever our function is computed by a vector line integral. Think of that vector line integral in whichever way you like. And if you look back up here to how it was stated in the first place, it was stated as the vector field is a gradient, and it was written as a vector line integral, and that would be kind of erase. That would be this version of the theorem. Yes?
Is the second one flux in the first one?
There's no flux.
Oh, no.
No flux here.
Yeah.
So I kind of skipped over that, and I am out of time now. So I tell you what, I'm going to talk about this oriented density and oriented size. I'm going to talk about this next time. And basically it's just a matter of interpreting, different ways to think about our integrands. We know our integrands are going to be densities in some sense, and a couple little details there. Okay, so I'm going to draw the line right here, but we will come back and talk about this orientation business on Wednesday. Y'all have a great day. See you on Wednesday. And as usual, stick around and make sure I mark you as